as in the basics. But before we take you through the basics, you have to know what threaded parallel computation is. And I'll be taking you through the first 4 as outlined, and Mayfield will take you through the last 4. So threaded parallel computation is just a technique that is used to enhance performance and the responsiveness of the applications. So before looking at those basics, let me take you a little through the key terms. Let me see the thread. So a thread is just basically a single unit of execution within a program. And for parallelism to be achieved, it can be achieved through the use of threads, which implies you have to use multiple tasks simultaneously to achieve parallelism. So these threads can exist within a process or through a shared memory. So the backbone of multitasking is threads. So meaning we shall look at the multi-threading, which can be the multi-threaded process, to perform those multiple tasks in order to achieve parallelism. So in my next slide, I'll be showing you the comparison between the single-threaded and the multi-threaded. So you can see from the first diagram, it is indicating a single thread that is being performed on a single processor, which can be the CPU. And the following diagram indicates multiple threads on a single processor. So it can be different cores, but within the same processor. So you can see they all share the same memory and they share other resources, but each has its own stack. The registers and the counters are all different. So the beauty of multi-threading, it can perform multiple tasks at the same time compared to a single-threaded process. So allow me to take you through, before that, I think now you understand what threaded parallel computation is. You perform multiple tasks simultaneously using multiple threads. So we shall look at the benefits of multi-threading, which is used in parallelism. So there is improved responsiveness, since the process involves breaking down that task. So it will also depend on the granularity of the problem, let me say the subtasks. So this responsiveness is improved because, let me assume, like an example, if you want to carry out, let me use maybe a chef. If a single chef is to prepare a certain meal, as in it is a single chef performing the cooking by himself. So meaning he'll have to carry out step by step, let me say, to cut onions, cut tomatoes, you know, the ingredients by himself. But when there are multiple chefs and they divide that work, the work becomes easier and it reduces also time. So the responsiveness at which the task is done easier. So when you move to the next benefit, it is efficient resource utilization. So multi-threading enables better utilization of the system resources, basically the CPU cores, by allowing the multiple threads to run in parallel. This enables us, like it enables the CPU or the task to maximize the resources that are available. So there is also resource sharing. Since the threads are within the same process or the same core, the same CPU, they share. But yeah, I already told you they share a memory. So this sharing facilitates the efficient communication and the data sharing within that process. There is faster execution, as I used from the first example for chefs. Since now the work is being divided into multiple threads, so these threads can be executed concurrently, and the total time that is supposed to be used, let me say, as in the first chef, the time which will be used by the first chef, who is a single chef, will be different from the time when these multiple chefs combine the efforts to perform a given task, which is cooking. There is that reduction in the time. So it means there is faster execution. So let's move to the challenges. The challenges, there is increased complexity. So when it comes to writing and maintaining them, the multi-threaded programs, there is more complexity in multi-threaded processes than the single-threaded processes. Then let's move to the concurrency issues. As you know, these issues, there can be the race conditions, the deadlocks, and these arise when multiple threads access the shared resources without the proper, let me say, the proper synchronization mechanisms. So this leads to maybe, let me say, difficulties in debugging the errors. So can move to resource contention. This occurs when like multiple threads are competing for the same resource. So this competition can lead to reduction in performance and also inefficiency. So we can look at the synchronization overhead. These overheads, they can prevent race conditions. The overheads can reduce performance, besides synchronization being a technique that can be used to reduce the hazards. It can also include the overheads. So these overheads reduce on the performance of the task or the process that is being performed. So moving to the next slide. Now we are looking at those basics of threaded parallel computation. So you look at problem solving. So problem partitioning, of which problem partitioning can also be defined as decomposition, because it involves breaking or partitioning of the task, dividing the task into smaller, manageable tasks, subtasks that can be executed concurrently using the multiple processing units. So from the diagrams you can see a single problem is being broken into different subtasks, but the assignment is on a single processor. Then the next diagram indicates a problem is being subdivided into different tasks that are being assigned to different processors. So the aim of problem partitioning is just to ensure there is high performance in the task. So moving to the next slide, these tasks into which the problem is decomposed may not be of the same size depending on the mechanism or the technique that you're using. And this decomposition determines the granularity of decomposition. So the choice of granularity impacts the efficiency and the performance of the algorithm. So we shall look at, let me give an example of a pizza. This is a real life example. So once you're given a whole pizza without being sliced, it becomes difficult to eat as in the whole pizza. You can't grab like the whole pizza at once. But once it is sliced, it becomes easier to choose which slice you can take. So meaning, since the pizza is sliced, it becomes more efficient for one to choose what to eat, but you can't grab the whole pizza at once. So its aim is basically to increase the performance of a task. So we shall look at the techniques of decomposition or problem partition. So we shall be looking at the decomposition techniques, and I'll take you through the recursive decomposition. So for recursive decomposition, it basically includes the use of divide and conquer algorithm, that strategy. So I'll just look at the example of a quicksort algorithm. So you can see from the slide, it is simply the breaking down of a problem into smaller, more manageable sub-problems. So we shall look at the quicksort problem, where you can see it is a sequence of elements. So what you have to do, you need to solve this problem. So when you look at this 5, you can see 5 is highlighted. So 5 acts as a pivot element, so meaning all the elements on your, consider your right and left hand. So when you consider your left hand, all the elements, it indicates the pivot element, means all the elements that are to be on the right, on the left, should be less than the elements that will be on the right. So meaning the pivot element, which is 5, will begin all the elements that are on the right. That's why you can see on your left you have all the elements that are less than 5, and the pivot element begins all the elements that are greater than or equal to 5. So all these tasks are subdivided. So for every step it is given an element. Now you can see on your left the highlighted element, the value of x is 3. So meaning all the values on that section on your left have to be less than 3, and all the values that are on the right have to be greater than or equal to 3. Same applies to this other branch. Let me call the first branch A and the second branch is B. So since our pivot element was 5, that's why you're seeing they are all values that are greater than or equal to 5, and the rest, it is also subdivided into tasks. So it is also given a value of x, which you are seeing it is shaded or highlighted, meaning all the values that are less than 9 have to be on the left branch of it, and all the values that are on the right of that sequence have to be greater than or equal to 9. So simply that's how a recursive decomposition is done, as the problem is solved using the quicksort algorithm as an example. So moving to the next mechanism, the decomposition mechanism, it is data decomposition. Data decomposition is just a method that is used for deriving concurrency in algorithm that operate on a large data structure. Decomposition of computations under this technique is done in 2 steps. As you can see, the steps are: the data on which the computations are performed is partitioned. Then, after being partitioned, the data is used to induce a partitioning of the computations into tasks. So you can see the partitioning of data can be performed in many ways. So you can partition the output of data, you can partition the input of data, you can also partition the output of data, both the input and the output, or the intermediate data also. So you can also look at the example as the matrix multiplication. The matrix multiplication, when it comes to partitioning the input, let me say put into consideration a 2 by 2 matrix. You look at a row by column. So the input, when you're multiplying, when you're solving the problem, since you're breaking it into smaller tasks, if you're solving the 2 by 2 matrix, you will multiply the first row by the first column, then you add the second row by the second column. That would be your first task. So you will continue multiplying, that is, as in the input, that's what you're inputting to be processed. So that is what you're feeding for it to be processed. So the processor will first handle the first row by the first column as the first task, then the second row by the second column, being broken into those small parts. Then I'll look at the exploratory decomposition. I believe the members who will be handling this part will explain more about it. The exploratory decomposition is simply the breaking down of a problem by searching through state spaces of a solution. So its aim is to explore the different configuration or the possibilities to find the optimal solution. So the example I'm using a 15 puzzle problem where you'll find there is one empty space, but it is on a 4x4 grid having 15 tiles. So one tile will be blank and the 14 will be filled. So you have to move tile per tile to make a complete grid. So meaning you will use different algorithms or different methods to fill that space. So the different methods can be the brute force, the heuristics algorithm, then the Manhattan distance heuristics. So you can go look at these different strategies that can be used to solve this puzzle. You can look at, maybe search on YouTube how this puzzle can be solved. So we also have speculative decomposition, which is the technique that is used in parallel algorithm, particularly when a program may take one or many possible computationally significant branches depending on the output of other computations that preceded. So you can see in this situation, when a task is performing a computation whose output is used in deciding the next computation, let me say, when you're solving a given mathematical computation involving brackets, the ANDing, the subtraction. So since you're following body mass, meaning you'll have to first handle what is in the brackets, and what is in the brackets will be used in the next calculation for a different operator. Let me say, after brackets, let me say that our computation has the ANDing and the subtraction. So meaning after handling the brackets, the results of those brackets will be used to AND, to be added. So meaning every computation that you get is used in the computation of another step. So that is basically the speculative decomposition. So we shall look at the hybrid. Hybrid just combines the different approaches of those other decompositions. Let me say from that example, you can see the first step, there is data decomposition. So there is the partitioning of the input, the output, and lastly, you see there is recursive. It combines all of them. So that is the final they follow. Like hybrid basically combines different decomposition techniques to solve a particular task. So we shall look at the hazards of concurrency. But before, you have to know what concurrency means. As you can see, concurrency is simply the ability of a system to execute multiple tasks or processes simultaneously. So, besides the benefits of concurrency, it also arises certain conditions that makes performance degraded. So these hazards arise due to multiple threads or processes executing simultaneously, leading to the different conflicts. So these are the different hazards that occur during concurrency. There is rest conditions. So these rest conditions occur when multiple threads are trying to access the same data, but then the outcome will just depend on the timing of the thread that will get there first. Let me say an example as for the athletes. They are all targeting to reach the finishing line because they all need one prize, you get. So the aim is to run faster and win after that when the aim is getting that prize. So the timing, the one who reaches the finishing line first gets the prize. So this leads to errors. Let me say these race conditions can lead to errors or the inconsistencies in the program. So these race conditions occur when the outcome of the computation depends on the relative timing of a concurrent process. So it will depend on the timing that is assigned to each thread or each process. So there is also deadlocks. So deadlocks occur when two or more processes are waiting indefinitely for resources held by each other, preventing any of them from progressing. So a deadlock just occurs when the two threads are waiting for resources that are also held by each other. Let me say, put this example. People are trying to open, let me say, the doors. Let me say 2 doors that are locked. So one person will need a key to open the door, which can also, let me say, these doors are having the same key. So one person will require opening the door first before the other one opens. So the other person, let me say the second person, for the second person to open the door, the person has to first wait for the first person to finish opening so that the second person can also access the key and also open. So this may result into miscommunication, maybe due to the method of synchronization that is used. There is also starvation that occurs when a thread is perpetually denied the necessary resources to proceed as the result of scheduling system. Let me put it in this way. There is, let me say there is a busy restaurant, so a waiter keeps getting assigned all the tables, all the new tables, while other customers are waiting. So this starvation, when this person is assigned every time given new tables, other customers will keep on waiting, and this, since it is a single person working on multiple customers, it will keep the customers waiting, since it is hard for the person to handle all the customers at once, which might overwork the waiter and also keep the customers waiting. So this can lead maybe to unfair scheduling. Or let me put it in this way. There is what we call scheduling the system. As you all know, I believe we covered these forms of queuing, the priority queuing, the weighted fare, So when you look at the method of scheduling, let me say if there is priority queuing, meaning only the people who are of high importance, let me say, in this case we are looking at data. The data that is of high importance will overlook the data of low importance, meaning before the priority data is handled, the low data will keep on starving. So in case of, let me say, any technical problem, these low priority queues will not be handled, because the first queues which are of priority, which let me say might be bulky, are not handled to be completed. So unless these priority queues or tasks are handled, the other low priority queues cannot be handled. So also, let me say, using this live example, let me say you all have bank accounts. Imagine you are in a queue and there comes maybe a minister. So I believe you all know they will not allow the minister to sit and wait for all of you guys to complete. What they will basically do, they will pick up the minister. The minister first does what he or she wants. Let me say maybe if you came for a withdrawal or anything, or let me say for any services at the bank, the minister will be handled first before all you guys, even if you came earlier, will be handled. So meaning they are starving you people who are of low priority and giving chance to the people of high priority. So that's basically starvation. And then I'll look at the live locks. These live locks occur when two or more threads continuously change their state in response to each other without making any progress. There are different stages of these threads. There is the running process, there is the waiting, and the blockage. So these states, they're running the different threads. Other threads might be executing, which is the running. Others might be waiting, maybe waiting to allocate the time that is for the scheduler. Then others might be blocked, meaning they're waiting for other resources, or they are waiting for other operations to finish for them to be performed. So once these continuously change, they might lead to miscommunication among the threads themselves in the process. So this might be similar to the deadlocks, but the tasks continuously change their state in response to each other without making any progress. But for the deadlocks, the deadlocks can even be they can be processing when they're in progress. But for the live locks, these ones, they result they occur as a result of the continuous change in their states. So another basic of threaded computation was locking. So locking is just the synchronization technique or the concurrency control mechanism that allows at most one thread or process to access a shared resource at a time. So this locking is basically used to control those concurrent hazards, as I earlier showed you. In the previous slides, there was the mutex, the read-write locks, the semaphores. So those concurrent hazards are different. Those concurrent hazards are solved using these locking mechanisms. So there are different techniques that are used to handle these issues, these concurrency issues. So let's look at the first one, which is the mutex, which is mutual exclusion locks. So the mutex allows only one thread at a time to access a shared resource. So it provides two operations. As you can see, there is the locking and the unlocking. So once a thread is being processed, meaning the other threads will be locked until the first thread has finished performing its task. Then once it is done performing, it will unlock for another thread to access the resources for it to perform its given task. There is also the read and write locks. This allows the concurrent read and access to a resource, but exclusive write access. So when you say concurrent read, meaning multiple processors can read, and the exclusive write, meaning only one processor can write at a time. So these locks are normally occur when there is maybe an increment in the read and write. So once there is an increment, in the task, meaning one will first be performed and then blocks, let me say, it blocks the other process, and it can only unlock when the other process, the previous process, is done. So there is also the semaphores. This controls access to a resource by maintaining a counter, allowing a specified number of threads to access the resource simultaneously. So this basically allows a given number of threads depending on the algorithm that is used, that is defined. So my last basic will be the locking contention. So the locking contention refers to the situation where multiple threads or processes are competing for the same lock. This leads to performance degradation. So what causes these lock contentions? So I have already looked at what locking is. So this locking contention means the different processes or the different threads are all competing for the same lock. So the cause of these lock contentions is due to the high frequency of access. Let me say there are multiple threads, like multiple threads that are accessing the resources. So the frequency, just the rate at which these threads are accessing a given memory. Then the long lock hold times. So you can see from the locks, it simply indicates the waiting, like once the processes are being handled or the threads are being handled, it is only one thread that is handled at a time. So once these are allocated, let me say, they are long awaiting times, it results into this lock contention, since they are all competing to get the same lock. And since this thread is taking long to be executed, it results into this competition. So the coarse grind locking, as I told you, parallelism will also depend on the granularity of decomposition. So if there is a coarse grind task, meaning the tasks are divided but the rate of granularity is big. Let me say, you put this example, let me say the sand soil, sand soil maybe, and loam soil. So when you look at the texture, basically look at the texture of something. So you find when the other one has more particles, bigger particles, sand soil has bigger particles, and this loam soil has fine particles. They are fine, like they are fair. So the rate at which, if you're to pour water, the rate at which the water will pass through the sand will not be the same. Sorry, let me not use sand. Let me use sand and clay. The rate at which the water in the clay soil will pass through will not be the same at which the sand soil will pass through. So meaning the granularity of a task also determines the rate of parallelism. So if this is coarse grain, meaning the the size of the tasks are bigger, it will lead to it will slow the rate of parallelism, like the rate of execution, which may bring about the lock contention. So the poor lock management, depending on how these locks are being managed, if it is managed poorly, so it will bring about this competition of these locks, the competition of these threads for the same lock. So but this can be solved through the fine graining, that is solving the coarse grain, the lock free algorithms, the reducing lock hold time, and the read locks. So this is what I had for you for today. Then let me invite my next presenter to take, next fellow to take you through. Thank you.
Crashing refers to the situation in the computer system where excessive or more time is spent on handling the system over it instead of executing useful work. So this can occur when there is high contention for resources such as central processing unit, memory storage, or disk input and output. The example of the crashing is like multiple threads running simultaneously. Imagine a parallel computing system with multiple threads running simultaneously. If these threads are constantly being switched back and forth by the operating system maker or developer without making significant progress on their respective tasks, then crashing can occur. So the advantages and disadvantages of crashing. Disadvantages: improve on scalability. Understanding crashing can contribute to the better scalability of parallel computing systems, allowing them to handle larger workload effectively. And the second one is improve throughput. Crashing can lead to the improved throughput as more time is spent on actual computation rather than on overload tasks like context switching and so on. Then the side of disadvantages is like decreased performance. Crashing can significantly reduce the performance of parallel computing system by increasing overhead and reducing the time spent on actual computation, and resource wasted and complex debugging. Excessive context switching due to the crashing can lead to the wastage of system resources, impacting overall efficiency. And identifying and resolving issues can be complex and time-consuming, requiring analysis of system behavior and resource utilization. And the third, another basic trait of parallel computation is privatization. Yes, privatization. This refers to the technique of reducing contention of shared resources by creating private copies of variables for each thread. This means that each thread has its own separate copy of data it needs to work with instead of sharing a common resources. For example, share variable. In parallel computing application where multiple threads need access to the shared variable, privatization involves creating private copy of that variable for each thread. This ensures that each thread operate on its own copy without interfering with others, thus reducing contention and improving performance. Advantages and disadvantages of privatization. Advantages: one is simplified programming. Privatization simplifies programming in parallel computing by minimizing the risk of race condition and other centralization or like all mediation related issue. And the second advantage is improve performance by reducing contention over it and avoiding costly centralization operation. Privatization can enhance the overall performance of parallel computing application. At the side of disadvantages, we have increased memory uses. Increased memory uses. Creating a private copies of variables for each thread can increase memory uses, especially when dealing with a large dataset or multiple threads that needs more memories storage. Then the second one is potential data inconsistencies. Improper implementation of privatization techniques can lead to the data inconsistencies if updates made by one thread are not reflected in another copy. Then the next basis of threaded parallel computation is fault sharing. Fault sharing occurs when multiple threads unintentionally impact each other performance by modifying different variables that are stored on the same cache line in memory. For example, two threads working on different variables. Imagine two threads working on a different variable that happen to be located on the same cache line. Thread A, supposing thread A update variable x, while the thread B update variable x, y. Since y and x share its cache line, any modification made by one thread can invalidate the cache line for both variables, causing unnecessary communication delay or centralization. Then disadvantages and advantages of the fault sharing. One is advantages: efficiency. Fault sharing can sometimes be beneficial if multiple threads actually needs to be accessed and modify the same data concurrently. Awareness. Understanding fault sharing shall help developer optimize their code for better performance. Like when you know your code very well and you can make it to the better performance. Then the other side is disadvantages of performance degradation. Performance degradation, unnecessary cache invalidation can lead to decreased performance. Then everything is degraded in the fault sharing. Then the last one is complexity. Detecting and resolving fault sharing issues can be challenging and time consuming, making it conflexible for the user. Then the last one is serialization. Serialization, this involves enforcing a specific order or sequence of execution for tasks or separation in parallel computation. By serializing a certain part of the computation, developer ensure that the critical sections are executed sequentially rather than concurrently. The example of serialization is application serialization. In a multiple-threaded application, serialization can be used to ensure that critical tasks or work are executed one after another instead of simultaneously. This can prevent race collision and data inconsistency. Then, advantages and disadvantages of serialization. The first one, simplify serialization or mediation. By enforcing a specific order of execution, the developer can avoid complex serialization mechanism. Then the second one is data consistency. Data consistency ensures sequential execution of critical sections, reduce the likelihood of data corruption and loss of data in the system. Then the set of disadvantages of reduce parallel. Serialization of the tasks limits the degree of parallelism achievable in the system. Then the last one is scalability limitation. Scalability limitation, overuse of serialization can hinder or hide the scalability as it restricts concurrent processing capability in the system.